Hello and good evening, everyone, and thank you all for joining today for the second session today evening. I am Devesh Lati, the program manager here at the Next Genius Foundation. The Next Genius Foundation is a registered charitable trust in India, and we help students with scholarships for their undergraduate education in the US. So all of you who are in grade 12 or gap year, I invite you to check out our website, which is next-genius.com, and learn about our scholarships. That said, today we have with us Dr. Erkan, who is the associate professor in the Department of Computer Science at Ithaca College. Very welcome to you, Professor Erkan. And we have Sandy Kelly from the admissions office at Ithaca College. Hello, Sandy. Welcome to you as well. And in today's session, all of you are going to learn about how a degree in computer science is structured across the 4 years, and what are the typical jobs that computer science graduates do, what is the future of computer science. And yeah, so I invite all of you to just make the best of this opportunity and ask your questions using the Q&A feature. And yeah, so a very warm welcome to both of you today evening, and we're delighted to have you here today. Over to you, sir.
Thank you. So how should I, would you like me to share the link, or can I just share my screen?
You can share your screen, yes.
Okay, let me do that now. Okay, so I'll put this in presentation mode.
Yeah.
And hopefully you could see the very generic science banner as well as me in the corner.
Yes, it's perfect.
All right, awesome. So, well, thanks for giving me the opportunity to talk about this, because I actually do care about my discipline, and every opportunity I get to talk about it, it's just a good thing to do. So I was given a number of things to cover. For instance, how is it structured at a college in the United States? What should students be on the lookout for in terms of opportunities, in terms of how do you succeed in this field? So basically, off of those prompts, I did the best I could, but I also want to say to you that I was born and raised in Turkey, and the school system here is rather technical. And I went to the United States for a college degree and then graduate years and eventually an educational career there. There was an interesting learning experience for me, which was a slight different take on how education is best conducted. So given the fact that my audience now is an international audience, I did also tap into those things a little bit. And in fact, I think that even sometimes in the United States, these are valuable points to share. So I'm hoping that there will be some utility in me going over them. So outline is basically this. Some of these things, the information is rather easily accessible. So for instance, I will have one slide that shows you the dependencies of the courses in a typical computer science degree. I won't spend too much time on those things, because any information that is easily accessible on the web, I think that it is best to simply point to them and then move on to things that are not necessarily accessible over the web. But still, I will commit to this outline as much as I can. And you'll see that some of them are longer than others, because sometimes when you get to the last one, for instance, comments on future trends, I don't think I would ever make the mistake of pretending to predict what the future is. I will share a few thoughts, but there's only so much one can say in such a dynamic field. So I have basically some reservations, as I said this in the slide, as I move to the next slide, which is basically I have to give you my credentials. So now I never do this, ever. The only reason I wanted to do it here is because at least half the slides are opinion-based. So had it been not opinion-based, let's say that I'm doing a lecture, the authority is the book. If I am presenting one of my research projects, that thing has been vetted. We had a hypothesis, we worked on it, we confirmed our conclusions, and so on. So it's never about the person delivering the message, it's about the science. But this is a little different. So I'm going to, for instance, that last bullet was my prediction about what might be coming up in the future. And since that's a rather subjective opinion, I thought that you might want to know who I am with and what I've done. So, and I guess the one that I care about the most is the first bullet, which is the number of courses that I've taught. And I actually take pride in that because as I started as an educator, it was important for me to get a sense of the different courses that one might encounter in a US institution, so that I would have a holistic idea of how education is conducted in general and how computer science education is conducted in particular. So going back to this, I thought that it might be best for me to sort of bundle the first and second bullets into one, which is what is the structure of an academic curriculum in a 4-year period in a typical US college or university, and then what are some of the concentrations within them, because those two go hand in hand. So I started with the thing that I know best, which is how we have set it up in my institution. And I won't focus too much on our details, but I will actually point to what seems to be generic. So in other words, what we do that is also the same as other institutions. So this is just a slice of the courses we have. So anyone who plans to get a computer science degree in a US institution will encounter a map like this, or some will call this prerequisite structure or a dependency graph, or different phrases to mean the same thing basically. And the way we read them is from the bottom up. So in a conventional US computer science degree or a related field, you start with principles of CS, then you move on to principles of CS2, and then that fans into a few other courses. So from institution to institution, you will see this structure, but you might see some differences. So this basically, these 4 will be pretty universal. So anyone who intends to get a CS degree in the United States will definitely see these 4 courses. The first 2 will be a year-long sequence that will expose you to the fundamentals of the field. And then the next one, data structures, the third one, is going to teach you some of the most fundamental tools we use in constructing software. And then the fourth one, algorithms, is when you become kind of like a language agnostic problem solver. So I love that phrase. It's not mine. I don't know who I borrowed it from, but it's a good phrase because it's language agnostic in the sense that by the time you get to that point in a computer science curriculum, what language you use is not really the point anymore. You have become a problem solver. And for that reason, basically every accredited program in the US or anything that is close to being accredited will have the sequence with the eventual target of making you a problem solver, which is articulated very concisely and concretely in this algorithms course. So then you will also see almost at every institution these 2 highly supplementary courses. So the one at the bottom is going to teach you the type of mathematics that computer science tends to use more often than other fields within the field of mathematics. And then there's this other thing called organization, which will give you at least 1 semester's worth of understanding how the systems on which we practice our skills are constructed. So the blue ones you could imagine are your training to be a problem solver using a programming language or a computer system. The lower orange box is going to teach you the mathematics that we typically use. And the top one is, since now that we know the math and the problem solving skills, how to design one of the machines on which we put these things to practice. So moving on from this, I thought, again, to make this presentation as general as possible, the link that you see at the top is for anyone who wants to get educated in computer science in the US, bookmark that. So that's basically a page where authorities in computer science education nationally in the US have gotten together and have made recommendations about how a computer science degree should be designed. And I had a little bit of a screenshot because I just wanted you to understand what are some of the subdivisions they have identified. So for instance, when I go back to this is how we have our courses in my school. Cornell has something very similar. Other schools will have something similar. This is basically a more comprehensive and universal look on computer science and computer science education. And the divisions they have here is a good indication of what are some of the subfields within the discipline. So if I go, and I remember six basically categories. So computer engineering is one, where you are mostly interfacing with computer electrical engineers on one end and computer scientists on the other end, so that you basically become an expert on building the machines. Then there's computer science, which is my home. And I would, as a side note, I would like to point out that that word, that phrase, computer science, typically, if you sort of get in the rush of getting a degree, you're jumping from course to course, we tend to forget that those are two words very intentionally placed in there. So computer, because we are dealing with computers, but that other word, science, is one of those important things that should always be on your radar. So when you become a computer scientist, when things work well, you're also becoming a scientist. And sometimes this gets forgotten. And I consider that to be one of the things that for which we have to be careful. So then there's cybersecurity. And actually you could see, now if you go to that link, you will be able to click on whatever appears to be a link, and you will get a fairly extensive document about how these authorities, this curriculum group, have gotten together and have defined them. And from the dates of release, you can see which ones tend to be younger than others. So cybersecurity became a standardized branch within this page in 2017. That's the only one. So you can see computer information systems go back a little bit more. Computer science goes back even further. And then there's information technology, which the earliest was 2008. And then there's software engineering. Yeah, I think so. I'm counting 1, 2, 3, 4, 5, 6. So I would say that this is a fairly reliable way to see the subdivisions within computer science or related degrees. Again, I leave this with you as a resource so that depending on if you browse them and understand exactly what seems to be the focus of each of these 6 subdivisions, you might be better assessing about your interests. So for instance, if you're interested in cybersecurity, definitely that's going to be a noticeably different curriculum than a generic computer science degree. And it's good to know that before you actually just venture in this curriculum, in this major. So I also wanted to share something that I borrowed from a friend of mine who teaches at Bryn Mawr College. And at their institution, explicitly, and at other institutions, included mine, sort of implicitly, we also have a different perspective on computer and computer science education. So I guess what I would like to point out is that interdisciplinarity is very important. I consider this to be one of the most awesome things about computer science because, as I said, computer science, we are a science. So we can propose hypotheses, we can conduct experiments, we can confirm or reject whatever hypotheses we had. So we can definitely call ourselves a computer scientist. But what seems to be spectacular about computer science is that we are also able to provide tremendous service to others. So some of the easy ones to understand. Physicists are in need of computational systems to actually conduct their own inquiries. Biologists, chemists. So all the natural sciences are definitely in need of the computational power that comes from these machines. So interdisciplinarity is important. And then once you dig a little deeper, you realize that that need is not just in sciences. I personally collaborated with historians for digital humanities or computational humanities or computational history, or in business. So this is a reality that we are now making use of in our educational system. So you could see that interdisciplinarity is emphasized from the get-go. We expose the students to the discipline early on, then we keep reiterating this pattern. And then the third one, humanizing of core CS courses. This is long overdue. We are in command of tremendously powerful machines. And I'm glad to say that as of late, we are now more aware of how we can use them to solve problems that mean something for humanity. So as someone who's going into computer science, maybe as a high school student who may have been exclusively thinking about the very technical aspects of the discipline, this is something that I believe should be on the radar of every student. again, we are in command of a very powerful machine, and there are so many ways we could make use of it, so many ways we could serve humanity. And now in at least some of the educational systems in the US, this is becoming a thing of emphasis. And also breaking down rigid boundaries. This also goes back to the slide that was previous to this, which is that ACM's classification of what constitutes the subfields. It's actually very difficult to partition the field into proper compartments because sort of everything overlaps with everything else. So one of the other trends that you will notice in computer science education is that we are no longer forcing our content into well-defined courses, but we are actually understanding that there are no rigid boundaries among these seemingly different topics, and we are trying to convey that to our students. So I would consider all of these things to give you some sense of what the structure of a computer science degree is in the United States. I don't know if I should pause here to get some questions, or and I would actually, so Devesh, do you have any suggestions? Should I wait, or should I just wait until the end?
I think let's take the questions towards the end.
Sure. Okay. And also, I just want to make sure that I'm not over time. Okay, so in terms of careers, this is basically, it would be mostly a reiteration of the ACM classification. So if you are getting a degree on cybersecurity, then obviously you'll be going in that direction. So those slides will give you some indication as to what careers are available. But I still did a Google, and I sort of like, I have my own thoughts, but I did look around a little bit, and these basically are the types of jobs that seem to come up a whole lot. So there's the web development, there's systems analyst, network architect, software engineer, and so on. I mean, this is actually a long list. I sort of had to trim it to make it fit into one slide. And I would say that no matter what seems to be going on, this is one of the luxuries of being in computer science, that because this technology is so embedded in how we live now, and there are so many opportunities in the future for a computer scientist, there's always some stimulating and satisfying job, and you could see a short list of many of the ones that exist out there. So I thought, let's actually dig deeper into one of them. I mean, are these just one phrase, just a phrase that might mean a course or not? Let's pick database administrator or database systems or database designer and so on. If this had been your interest in a computer science degree, you would, in a contemporary computer science degree that does justice to the field, you would definitely spend time on understanding what is the right way to structure large-scale tables of information, how these integrate with each other, how can you propose a question that draws its answer from various different tables along the lines of how those arrows are drawn. So I know that this is actually too detailed for me to give you a sense of it, but I just want you to understand that when you are designing a database, you're breaking it up into pieces, then you're exploring how they could be put together to answer meaningful questions. You would then be learning about the tools that database people use to actually be able to do their jobs. So there's a particular screenshot from one of the many tools that one can use. You would learn how to interface with a database. So even if you are a software engineer or a mobile developer or a web developer, you still have to be able to talk to a database that will most likely be sitting on a standalone machine somewhere on the internet. So then there's the programming aspect of how do you get to it, how do you ask your questions, and so on. Now, there are emerging technologies. The database that dominates the world has its roots in the 70s, but now there are other types of databases that are of relevance. So Mongo being one, preferred by web developers. So you would have to get some competence in those. And then there's also different, in addition to some of the things that were needed for web developers, there are entirely different architectures. So for instance, you could actually see your database as a network. So you can imagine that, I want to go back to this list. This was a very high level list of what one can do in the field. You just dig a little bit into one of them and you go into this own universe of all the incredible things you could do. So I could do the same thing basically for any one of these things. So if you are making a decision about your major, I would say that perhaps the best thing would be to go back to ACM's subfields within computer science, see which one interests you, then find jobs that are actually serving that particular subfield, and then try to understand exactly what courses will teach you if want to gain competence in the subfield that you have chosen. So now I want to go back to traits and interests the student must possess to do well. So this is basically now I am going to be transitioning to those things that might be a little harder to find on the web. And this also is going to be focusing on what I had to learn as I transitioned from one type of educational system, which was very technical, to one that is more general, that eventually allows students to sort of explore the options, discover themselves, and then apply themselves to whatever seems to satisfy them the most. So, but before any of that, I actually looked at this bullet. It says traits and interests a student must possess, there's a typo there, sorry about that, to do well. So I think the reason I hesitated when I looked at this bullet was because it gave me the impression, which I have seen everywhere, that there are some students who are more likely to be successful in computer science, and there are some students who are less likely to be successful in computer science. So for instance, traits, right? So that's a word that implies what you are born with or what you have maybe instilled up to the point of college. In my experience, this is really not true. I think that the best word I could use as a substitute for this was approach. I want to go back to my statement about the importance of applying computer science to meaningful problems, no matter where those problems come from. So I no longer prefer to see the world as those who are necessarily gifted at this or can do this, but I see this as people who want to make a difference. And anyone who wants to make a difference can actually be a good computer scientist with the right approach. So these are some of the things that I've seen over the years. This was the reason why I had my credentials slide, because I just want you to see where this idea is, where these opinions are coming from. And I thought of basically 3 distinct things that I would advise any of my advisees at my home institution to be mindful of to do well in computer science. And you will see that none of them have to do with being good with numbers or being good at memorizing things or being a very logical person. These are things that are skills and that have to do with attitude and approach, which means that basically anyone, if they have the right goals, if they have the motivation, can actually do well. So knowing the real challenge that comes with the discipline. So that's actually a very ambiguous thing, and it's actually a very specific thing. I have a bunch of slides on that. Then finding the right learning environment, and then having the right perspective and the right engine. And the reason I have that word engine in quotes is because it's not really like an engine, but it's kind of like what powers you. So let me actually start with the first one. And even if this, so what I'm going to say to you is not going to apply if you go to this school versus that school. It's going to apply every school. In fact, it's going to apply to almost every discipline, not just computer science. But I consider this to be one of the most important learning experiences for me. So we won't be able to interact, but if this had been a lecture, I definitely would have asked you the following questions. So I'm going to show you a series of slides. And each of the slides will have a progressively larger sort of network where everything is connected to everything else. And my question to you would have been, what is going to be the connection, the formulaic connection between the number of nodes you're seeing and the number of lines and the number of connections between those nodes? So the word node, in case you haven't actually seen it before, it's basically, I could have said things. So there are 2 things here. So technically those are called nodes. And you see only one connection in there. So again, if this had been a lecture, my question to you was, as I show you these slides, try to figure out what is the formula between the number of nodes and the number of connections, okay? So with 2 nodes, there's only one connection you can make. With 3 nodes, there are 3 connections you could make. With 4 nodes, there are 6 connections you could make. And I'm going to give you a second to make sure that I'm not lying, right? So there's basically kind of like that diamond around the outside, and there's a plus in the middle, so you can count the lines to be 6. If I add 1 more node, you'll see that the number of connections goes up to 10. So I don't know if you're keeping track of this, but basically the number of nodes are growing by 1s, and the number of connections are growing by faster steps, like bigger steps, right? Progressively getting larger. And the last one I'm going to show you is with 6 nodes, you have 15 connections. So let me just quickly go through them so we can see the progression of the number of connections. So the first one was this. So 1, 3, 6, 10, and then 15. So I won't be able to hear your answers, but I'm wondering if anyone can figure out the number of the connection between the number of nodes and the number of connections. And I will explain to you why this matters, but I just want to give you like 5 seconds to think about that.
And I've also actually opened up the chat box, so students, you can also write it in the chat box.
Oh, sure. Yeah, I'd be happy to see that. Although, actually, would you mind telling me if someone puts an answer because I have the slides maximized?
Yes. So students are saying, someone is saying NC2, which is a combination formula. Someone is saying 21. The number that adds up increases by 1. Okay. N into n minus 1 by 2. Someone says that is the formula. N into n minus 1 by 2.
Yeah, okay,
21.
awesome.
Someone says arithmetic progression.
I have a very technical audience. Okay, so that's good. That's actually exactly right. So let me ask you a much harder question since you seem to be on top of this. Can anyone guess, and I really would love it if you put your guess in the chat box, what is the point of this? So you clearly understand the formulaic relation between the number of nodes and the number of connections, but what could be my point about this and computer science, both its education as well as its discipline? It's okay to be wrong, by the way. So if you have a thought, doesn't matter if you're thinking maybe, maybe not, just go for it. Just share it with us.
Problem solving, computational thinking, to assess the number of connections in network topology. Again, problem solving, logic, neural networks.
Okay, good. So these are actually, these are fine answers. The thing that I was going for was a realization that happened to me in the middle of a lecture, actually. And so let me share it with you. Basically, one might say, well, this is an abstraction, right? So, but what do I actually mean by the nodes? So in which case there's like 6 here. So if you are writing a computer program, and let's say that you have one single file, let's say you're using Java, and you have like 1,000 lines of code in one program, and needless to say, you will have multiple methods. So in this visualization, you could say that in my Java code, each node represents a method. And if there's a line from one method to the other, that means that one can call the other. And I'm going to refer to this as an interaction. So any method can interact with any other method depending on how you make use of them. And ultimately, what determines the correctness or flaw of a program is going to be what happens in the interactions. Okay, so that's why it is so important to understand that even if you add components one at a time, the number of interactions go up by the square of the number of nodes. And the thing that matters is the set of interactions. So if you say that, okay, it's not my Java program and the methods, but these are the courses in a computer science curriculum, once again, you have one more course, but the way that what you learn from that class will interact with everything else you've learned in other classes will go up by the square of the number of courses. So if you are a full stack developer, which is basically someone who sort of knows enough about every component that he or she will have to use to make an operational system, you add one more component to your full stack development set of expertise, and the number of interactions will go up by the square. So I would argue that definitely for computer science and for learning in general, the main challenge has to do with the realization that what we are dealing with is a system. So it's the system could be the curriculum. The system could be this piece of software. The system could be the set of tools you are using as a full stack developer. The main challenge in computer science in particular and learning in general is that it's all about the interactions. So if you engage your education with this mindset, you will graduate a very different person than someone who simply focuses on the nodes. The difficulty is not what's happening within the nodes. Those are actually simple pieces, well-defined pieces. The real challenge is the way these things interact. And if you keep this as your compass in dealing with what you encounter, you become a noticeably different person as you graduate. You will not be expecting your teacher to tell you this is what is happening in this class. You will get it and then instantly start thinking about how it relates to other things. And anyone who can do this definitely does well. So then the second thing is finding the right learning environment. Let me look at what time it is. Yeah, I'm sort of on target. This is, again, another thing that I don't necessarily think that there will be a slide out there, but what I learned as I transitioned from a technical upbringing in my middle school, high school years to the learning that I now appreciate and practice is actually have to do with less to do with the particular discipline, but more about some of these freedoms that we are afforded. So for instance, a student, no matter what they engage with, will do well if the environment allows them to deal with complexity, with diversity, with change, if they are able to delve into specific areas of interest as opposed to what they have been told to do, or to gain a broad knowledge of the wider world, to develop a sense of social responsibility, to acquire communication, analytical problem-solving skills, and finally to apply their knowledge in real-world settings. This makes a huge difference because when you know what you can do with what you're learning, and I think that anyone who's doing computer science is just so empowered to make a difference. If you are aware of these things, then you will want to do more. You'll be driven by curiosity, as you'll see in the next slide. And someone who is driven by curiosity, who is afforded a learning environment that allows them to do this, basically all educators will then have to do is to get out of their way. And then they will just roll and they will do everything that they want to do. So the third thing was there's a phrase that if you're interested is actually pursuing an education in the United States, you might actually see this liberal education environment or liberal arts. Now, schools that are not necessarily designated as such still will afford many of the things that come under that banner, but I still want to just allow you what I hear when I see that phrase. So a liberal education environment, especially for someone like who wants to be a computer scientist, the liberation will be from a fear of exploration. It'll be a liberation from the fear of questioning, a liberation from the fear of being questioned, the relation with constructive criticism, and searching for where you excel. So these were things that I learned over the years when I was a student and then an educator in the United States, and being mindful of these things, no matter what your field is, as technical as it could get or as humanistic as it would get, these will then allow the student to reach their potential. So then finally, those two things about having the right perspective and engine, I think that in computer science in particular and learning in general, if you see education as an opportunity and if you are driven by curiosity, again, you no longer feel the need to define what makes a good computer scientist, what skills. Basically, anyone who actually approaches this, who sees education as an opportunity and who's driven by curiosity, which will be afforded to you if you are in an environment like this, will then do great things. I've seen many, many examples of this. Last thing, comments on future trends. Oh boy, this is where I was afraid, like how could I actually make a prediction? I think that it's safe for me to say these things. So my high-level partitioning of the field in terms of what I anticipate seeing in the future, I would say that I anticipate seeing advances in these three different sort of buckets. So there's systems, right? No matter what we are doing, ultimately the software we produce or whatever we have that's running on a computer is going to be running on a system. So there will definitely be advances in the system, and so you could see the internet as a system, you could see robots as systems, blockchain can be as a system. In fact, that was one of the bigger ones. So these systems, as they grow, as they develop, they will make new kinds of software possible to run on them and to solve new interesting problems. So systems definitely is a field in which I anticipate seeing advances. Then problem solving with these systems. So what I include in that line would be your artificial intelligence, your machine learning, your good old algorithms, your programming languages. So once someone gives you a machine that can do incredible things incredibly fast, then you can apply all of those somewhat theoretical, but definitely practical also to solve problems. And then finally, interacting with these systems, because ultimately, these are not machines who are doing these things for their own sake. Ultimately, these machines are working with humans. We want them to solve problems for us. So interacting with these systems is also a field of interest. So I would anticipate most of the things that get my attention in the next 5 to 10 years to properly fall within one of these three things. And only on this beautiful thing that I could say about the past as well as the future of this field is the following. Nothing really seems to get obsolete. If you actually study the internet, you'll see that the underlying infrastructure initially was analog, and then it became digital. And then there was a reason for it to be analog again for reasons I won't get into. And then it became digital. So I don't think that it's safe to say that things become completely obsolete in computer science. The same thing, 80s and 90s, distributed systems, parallel systems, they were big deals. And then they were sort of like not emphasized as much. And now they are once again a big thing because now they can be afforded to end users in commodity types things. You don't need like a research caliber machine to have parallelism. It's basically the norm now. So nothing really gets obsolete. That's one thing that I expect to not change. And then the next thing is that everything gets obsolete. So if you anticipate that let's say that you're an A student, you get A pluses from, A pluses from all your courses for 4 years, you do incredibly well on your projects. If you stop learning when you are done in 5 years, most of what you know will be obsolete. So I don't know if you've taken physics classes that talk about how light, like light in the physics sense, has the dual property of like it's a particle as well as it's a wave. It carries both qualities even though they cannot really have both. I find this to be true in computer science too, that again, nothing seems to truly get obsolete, but then on the other hand, everything seems to get obsolete. So I think that this is going to be the one thing that never changes. Okay. So that's it. That's what I have. And I'd be happy to answer your questions.